before we move to gradient descent, I just want to give an example also on why having these hidden layers and having more complex neural networks allows to model complex functions. So for example, in the 60s, actually 70s, people were only using neural networks composed of, imagine that these are input neurons and output neurons. Basically, there was no hidden layer. It was from input to output. Again, here you will have a function like a softmax or sigmoid function or something like that. So in this case, for example, yeah, you would have something like a step function or a sigmoid function in the output layer, but you wouldn't have hidden layers. And there was a paper in the 69 that basically showed that you couldn't model certain functions through these neural networks only. For example, if you take the XOR function, which means the XOR function means that it's 0 whenever two values are equal, it's 1 when two values are different. So if your input variables are all 0, 0 or 1, 1, the result is 0. If they're different, like 1, 0, 0, 1, the XOR functions gives 1 in output. And this corresponds, if you have x1 and x2 here, means that you get. This is an example of the classification of why nonlinearity is important also in classification. There is no line that you can draw that is able to separate this. And also, in this implementation of the neural network without hidden neurons, there was no way in which you can draw a line or separate this function. Then once hidden layers have been added much later on, also because the algorithm that we're not going to see, unfortunately, to be able to identify how to change the weights to better model the data, basically the learning in particular, have been developed in the 80s. At the beginning, the implementation of the neural networks was only with input and outputs. So it was basically in the end almost a linear function. And they demonstrated that this couldn't be modeled with such a simple neural network. This created a lot of what is called as the first AI winter, in the sense that neural networks started to get less fundings because people thought that this was not a promising direction. Then after the 80s, these hidden layers started to be added, and that's where there's a second wave of interest into neural networks. We're also going to see an example of this in practice later on. But let's now see how it's, at least intuitively, how it's possible to find the right weights and biases to give the best output predictions in a neural network. And for explaining it, I'm going to give an example, which is also going to be the example that we're going to work on in the exercise session, which is also what is very related in what we do in our lab. And the task is going to predict cell types. Imagine that you take a sample from a lung cancer patient. Then there are some experimental protocols to measure gene expression of these cells, of all the individual cells in the sample. And so you will get a matrix of cells by gene, and the value of each element is how much a certain gene is expressed in a certain cell. In this case, we're going to consider only 100 genes, even though usually it's around 20,000 per human. And imagine that an expert came and annotated all the cells with the cell types that it belongs to, or the cell type that it is, based on which genes are activated. Usually, the way you do it is that you cluster cells based on their gene expression. Then you look at which markers characterize those groups. And then based on which genes are specific for those groups, you can see, this is a macrophage, this is a T cell, this is a cancer cell, and so on. And so imagine that an expert have annotated these samples manually, And so for every cell, you have the gene expression, which is the input data, and the cell type, which is going to be the things that we want to predict. So it's a classification problem in this case. Then imagine that a second sample comes, and again, you do the experiments, so you know which genes are activated for all the cells in the sample, but you don't have any expert annotation anymore. So you need to find the cell types for this new sample for which you don't have the labels. And again, learning means to find the right weights and biases to be able to do this classification accurately. And so what happens basically is that you're going to provide the input data to the neural network. It's going to try to predict which cell type it is based on the input data. And then based on how well or bad it scores, the algorithm, the way the neural network works is that it adjusts the weights and biases to try to make the prediction as close as possible to the real label that you have. So it's going to try how to change the weights and biases to be able to get macrophage, in this case, as high as possible, and all the others as low as possible. At the beginning, you initialize the neural network with random weights and biases. You put random values, and of course, the output is going to be garbage because there's no actual relationship between the input and the output. If all these weights here and the biases are random values, the percentages, the probabilities that you're going to see here are also random. Then what the model does during the training is that it compares the predicted output with the desired output. In this case, since this is a macrophage, you want to have 1.0 to the neuron corresponding to macrophages and zeros in all the rest. So you compare what is predicted, that for now is garbage, with what you want to get. And you need to kind of measure how well the neural network is performed based on the data. And so you need to use or define a certain loss function. Basically measures how good is the quality of your output with respect to what you want to actually get, the desired output. In case of classification, for example, the one very common loss function is the cross entropy loss, which is basically computed as the sum over all the samples. So in this case, we're assuming that we want to compute the performance in the sense of the quality of the output of the neural network for all the samples in the dataset, all the training samples, the ones that we had at the beginning on the left side. And so you sum for all the samples, meaning all the cells, for all the classes, so B cells, cancer cells, macrophages, and T cells, and you multiply the desired label, desired probability. So in this case, for example, for B cells, 0 times the natural logarithm of the predicted one. So here, for example, for only this sample is going to be 0 times logarithm of 0.1, plus 0 times the logarithm of 0, plus 1 times the logarithm of 0.4, and so on. And so this is an example. For example, the cross entropy loss between the vector 0, 0, 1, 0, which is the desired output, and 0.1, 0, 0, 4, 0, 5, which is the predicted one, as I mentioned before, is minus 0 plus 0 plus 1 times the logarithm of 0.4 plus 0, because every time you multiply something for 0 is always 0, and you get a very high score. Cross entropy, the maximum value that you can get is 1. You get a very high loss, meaning that the neural network is performing badly. But do you see a problem here in the sense that basically the cross entropy is ignoring all the values here? because in the end, in the desired output, they get multiplied by 0. So whatever the value we have here, this is not going to influence the loss. You think this is a problem or not? Don't be shy. You can say whatever you want. You're not going to be judged. You think it's a problem? If all this, that regardless of the value of the probability for B cell cancer cells and T cells, this doesn't impact the loss at all. Yes or no?
I would say no, because either way, the other values all sum up to 1, so even if the correct answer has a very low probability, it doesn't really matter if the other ones are, because they're all related to each other.
Yeah, that's exactly it. You wanted to say something similar? You want to add something? No.
It's just, I don't know, mathematically, that would mean that if we have 1 with the predicted value, we have 0.
Yeah, exactly. That, as both of you said, if you increase the value on 1, all the others will go down. So you can still optimize for this, and automatically all the other ones will automatically go down. So in the end, it's not actually a problem. You can focus only on the right and the loss based only on the correct output. All clear? Doubts? Okay. Another problem. What if the probability that was predicted here was 0? What would happen mathematically? What is the logarithm of 0? Infinity. So if the neural network by chance or for whatever reason gave 0 as a probability of macrophage, this loss, mistake. Yeah, this loss will go to infinity. I made a mistake before. This function is not, the maximum is not 1, could be infinity. Can you come up with some way to overcome this problem? How can you solve this problem? This is not necessarily obvious, but there are 2 solutions for that. It's just a detail. You can add a small constant value to all the predictions, so basically 0.00000001 instead of outputting 0. This will give a very big loss, but this will not go to infinity, so it's not a problem. Or you can do loss clipping. So you put a maximum value to the loss that you can get. And so if you put loss clipping to 10, even if it went to infinity, the loss will always be 10.
So what is the issue if we get it, would we just know that?
It wouldn't be possible to understand how much to change the weights, because basically there is no point of reference for the algorithm to update the weights. This is an example for a good prediction. So in this case, we have 0.9 for macrophage, 0.1 for B cell. And in this case, we see that the loss is lower. Then in case of regression, a very common loss function is the mean square error that you may have seen already multiple times, which is, again, the sum over all these samples, so over all the cells, of the difference between the desired output and the predicted output squared. So in this case, if you have, not read well, 2.5 as predicted output and 4.7 as desired output, for only this sample is going to be 4.7 minus 2.5 squared. So in this case, we are assuming that because you want to optimize the output of your neural network over all your training data set, not sample by sample. Otherwise, you're going to have a very partial information of how the neural network is performing overall. So what you do is that you compute the loss over all your cells and you try to, and the model tries to minimize this. In this lesson, we will not have time to see how to compute the changing weights, how you should change the weights and biases based on the loss function, because it will take a while. But if you're interested, that algorithm is called backpropagation. But it's basically a method to identify how to change the weights and biases based on the value of loss that you got. We're not gonna see that, and we're not gonna ask you about backpropagation. But conceptually, you just have to think about that. Based on the loss that the neural network gets, it will try to change the weights and biases to minimize this loss. So in the end, it's an optimization algorithm. We've seen some examples of classification for cells and biological and gene expression data. One possible application of regression is autoencoders. Basically, autoencoders are still neural networks in which instead of predicting a class like macrophages, T cells, tumor cells, you're trying to predict the input itself. So you take the gene expression vector of a specific cell, you pass it to a neural network, and the output is trying to predict the same input that you gave. The important aspect here is that the number of neurons that you have at the center of your neural networks need to be smaller. If you have as many neurons as the input, of course, you put everything to one, and then it's, of course, able to output the same input without any problem, but it's not learning anything meaningful. If you make it pass through a sort of bottleneck, you're enforcing the neural network of doing a sort of compression, trying to synthesize the information inside the data to be able to compress it, and in the end do dimensionality reduction, which is what you have seen in the previous lecture. And so you can do mean square error. You can compute the mean square error between your output loss to your output features and your input features, and see how much the neural network is how well it's predicting it. And by using this backpropagation, it's going to learn features which are meaningful, which are useful. So you do this for all the cells. You do this for all the cells multiple times, and the neural network is going to learn some meaningful features, smaller than the input one, which are able to encode as much information about the data, which is essentially the concept of dimensionality reduction. So it could be used to do dimensionality reduction, outlier detection, removing noise, imputing missing values. You can also remove certain values of the input and try to see how well it predicts those input values based on the other features and so on. You can generate data, so you can set whatever value you want in this part here, which is called embedding, and generate whatever output. So these are very used, like models which are used very often. And is also an example of how neural networks could also be used for dimensionality reduction. So it was useful to talk about it in the context of also of the other lectures. And so, for example, if you take, for all the samples, for all the cells, you take the vector associated with it. So if you pass the input of these cells, this is going to be activate certain neurons here in this bottleneck. And you can take these features and do it for all the cells in the dataset. You get a dimensionality reduced data. In this case, it's going to have 2 neurons. So for every cells, you will have 2 features. Then you can, for example, compute the UMAP based on these features, and you're going to see different clusters of cells based on the gene expressions that they have. So this is a common approach to the dimensionality reduction of the data.
What is the formula of the loss that you use in this process?
Yeah, it's the mean square error. So
Yes.
yeah, because it's still a regression. Where is it? Still a regression problem, because in the end, you're trying to predict continuous values. In this case, it's not gonna be only one, but it's as many genes that you have. So you're gonna predict all 100 genes in this case. And then, so it's gonna be for every feature, it's gonna be this minus this squared plus other feature, desired minus predicted squared, desired minus predicted squared, all summed up. And as I said, you're basically, the objective of training a neural network is to automatically minimize this loss function, because this is what we want. We have to have the lowest loss, because if the loss is the minimum, we know that the neural network is predicting the labels as best as possible. And if we take as a toy example, a tiny neural network that has one weight, and we don't even consider bias, so it's only one weight between the input and the output. In theory, what you could do would be to compute the output for each possible value of the weight. Here we're considering a certain range, but in theory, you could see what is the output of the neural network when the weight is 0.6, 0.5, 0.4, 0.3, and so on. Of course, this is expensive, especially if you have a lot of data, or as we'll see in the example later, you have many different weights. In this case, it's only one weight, and it's a toy example. It's easy to represent, but this is not what you do in practice. It's just a way to represent and help you to understand how these things work and how the neural network is able to find the right weights. And the way that you do it is that, imagine that you start from a random value of the weight, for example, 0. You compute the loss function based on the data that you have, and through that algorithm that I talked about, you can measure the slope, the gradient. So how much, in which direction should the weight change to be able to improve and minimize this loss? As if you've taken the derivative of a function. The derivative of a function is the direction of steepened ascent. So it's the direction in which the function increases the fastest. In this case, we want to minimize, so we go towards where the function goes down. So it's what is called gradient descent, not gradient ascent, in the sense that by computing this gradient, again, I'm not going to see how, but by computing this gradient, you get the direction in which you need to go to be able to lower down your loss function. Of course, in this context, because it's one weight and we have drawn the actual function, is easy. But if you only have points, this is not easy to do. And so once you have computed the gradient, you know that you have to increase the weight to be able to lower down your loss function. And so you move, then you recompute your loss function, then you decrease the weight up to a certain point in which the gradient is 0. Because wherever you increase or decrease the weight, the loss function here is going to increase. And so this is going to be considered as a minimum. As you can see, there are lower values, and so these are usually called local minima, while this is the global minima, will be the optimal solution. So it's possible that sometimes a neural network may be stuck to suboptimal solutions, and there are also approaches to overcome that. For example, one concept, also here I'm just going to give the intuition, is the concept of momentum, which is based on, the intuition is based on intuition of the physical world. So imagine that you have function like this, momentum is basically that once your loss is, when your loss goes down, because you're bringing the weight to a certain value, so in this case, you're increasing the weight to bring the loss down, even if it reached a moment, a place with zero gradient, it still has a little bit of momentum in the sense that it's still gonna keep increasing the weight a little bit to avoid getting stuck in local minimum of up to a certain point. But yeah, very conceptually, this is the concept of momentum, that even if the weight and that specific weight has reached gradient equal to zero, still going to keep trying increasing it a bit to make, because maybe this is just a local optimum. Is it clear? So this was one example with one single weight, so very simple neural network. Once you have two weights, like one weight and one bias, now you have two parameters. So it's not a line anymore. Now it becomes a surface. And again, areas with blue values, like more brighter values, they are corresponding to higher loss, while the wider it is, it corresponds to lower loss. So place where you want to set your weight on in the end. So for example, here the best solution would be to have a weight of around 0.7 and a bias around 1. And so again, by computing the gradient, you can see what is the best direction to try to lower this loss. And so you compute the gradient, you move, you do a little jump, then you recompute the gradient, little jump, and you change the weights until you reach a place where the gradient is 0. And so the point is not going to move anymore. As I said before, also here you can have local minimum and a global minimum. We've seen an example with two parameters, but of course, current neural networks are much bigger. Normally, in a normal settings and so on, as we will see in the exercise, you can have tens or hundreds or thousands of parameters. Current models like ChatGPT, GPT, or these all large language models can have millions, if not billions or trillions of parameters. So for example, GPT-4 was estimated to have around 1 trillion parameters. And so you can imagine that it's not possible to imagine these functions and represent these functions, because you will not have a line, you will not have a surface, you will have something more and more complex. And just to give some curiosity, like to give you some context on how large language models are trained. The way they're trained is basically trying to predict the next word. So it's basically a classification problem. The model gets all the previous words in a sentence, then it's supposed to predict the next one. So it's essentially a classification problem. To be precise, it's not predicting words, it's predicting what are known as tokens, which are parts of words. This has two advantages. One advantage is that, for example, you can represent concepts as part of words. For example, if you have, I don't know, unhappiness, you can divide the word in these three ways, and un will basically mean not. Happy is related to the concept of happiness, and ness means that is associated to the concept of happiness. That's why you have, I don't know, also for useful and useless. You can divide it into use, less, and use, full, and you can kind of compartmentalize your prediction into different concepts. The concept of use, and the concept of absence, or the concept of presence. So it's easier for the neural network to predict. There's also a second reason why predicting these is better than predicting words. Do you have some ideas on why? Remember that this is a classification problem.
By dividing them, you have more data to work with, because there's more words.
In theory also yes, but there's also one other concept that is more useful. How many words are in the English vocabulary? More or less 200,000. Then if you divide them into some words, you can reuse some of them, and so your vocabulary becomes smaller, 70,000. So it becomes an easier classification problem because you have to predict out of 70,000 possible alternatives instead of 300,000 possible alternatives. But your concept is also useful, like it's to keep in mind on why you should not, why in the end they don't predict letter by letter. Because in that case, the data will be too complex, like the sequences will become way too long to be modeled efficiently. And so that's why they predict some words instead of letters. Because in theory, letters are only 20, 30 characters, so it should be an easier classification, but since the sequencing are much longer, the space becomes way too much complex. So this is a nice in between. I'm not gonna ask you that in the exam, it's just out of curiosity.
Here we talk about parameters, we've seen weight and bias, but what are the other parameters possible?
At the moment, parameters means that weights and biases are basically the knobs that you can tweak to influence your output of your neural network. And as I've mentioned, the negative gradients give you how to change these parameters, so weights and biases, to decrease the loss function as much as possible. But again, we're not going to see how to compute this gradient. So this process is called gradient descent because you have to go down the gradient to lower down your loss. There is one other problem. Imagine that you have a data set of millions of cells, or in the case of large language models, of the whole text ever produced by society. Putting all this information inside your model, in your computer or server or whatever, putting all the data set all at once would be way too expensive from the memory point of view. There's no machine that can take inside in the memory all this amount of information. So what is usually done is that instead of computing the loss over all the samples, so all the cells in your dataset, you divide your dataset in small batches of 100, 1,000 cells. You compute the gradient only for that subgroup of cells of 100 or 1,000, and then you change the weights based only on the loss of these hundreds or 1,000. Then you move to the next group, you compute the gradient, you change the weights. Next group, you compute the gradient, change weight. And then when the average loss doesn't decrease after some iterations, then the training stops, meaning that hopefully the neural network would have reached the smallest prediction error. And this goes stochastic gradient descent because you're splitting the dataset into different batches randomly. So there is a stochastic component, which also means that your path to the optimal weight is not going to be perfect, because every time you compute the gradient and update the weights, it's going to be only on a smaller part of your dataset, and so the gradient may not be perfect. But on average, it's going to go in the right direction and end up hopefully in a similar spot. Okay? And so this is what happens. You compute the weights that you have. Through the gradient, you compute by how much you are supposed to change the weights. You just do the sum, and you get the new weights. And so these are the parameters. So the internal variables of the model, which are learned from the training data. Then there's another concept, which are hyperparameters, which are not parameters that are inside the model, but influences how you train the neural networks. Like the batch size, which is the size of these groups, of these batches that you take, the number of iterations for which you train the neural networks, the number of hidden layers, the number of hidden layers is a hyperparameters because it's not the actual weights and biases, but influences how many weights and biases you will have, the size of the hidden layers, so every neuron, how many neurons you have in a hidden layer, and so on. There are many, many different ones. And how do we choose the right hyperparameters? What is usually done, and this is important to know in machine learning and statistics in general, is also something that people tend to not do properly very often. Let me remove this. Yeah. Is that you should divide your dataset into 3 subsets: the training set, the validation set, and the test set. So the training set is what the model uses and sees to find the values of the parameters, so weights and biases in this case. The validation set, which is the data set that the model will see to find the best hyperparameters, so number of layers, how many neurons per layer, and so on. And the test set is the final evaluation, is what data you're going to use to say this model has an 80% accuracy. And this test set must be used only once. If you reuse the test set multiple times, you're basically trying to come up with the best solution for that specific subset of the data, but then would mean that if you get another data set, will probably not generalize well because you're trying to optimize on this specific test sets. That's why it should be used only once. And that's what people don't often do because they want to have highest value to be able to publish. And so this is an example of changing the effect of changing the hyperparameters. So this is the loss function on the training set for, also here consider it as a toy example. The loss function curve for the on the training sets for a neural network with 1 hidden layer and 2 neurons. The training loss goes down, which is good. Then it starts to converge. And this is the validation loss. So the validation on a set that as a group of cells that we set aside only to evaluate how the model is going. And so this is also going, at some point it's kind of converging. If we increase the neurons, so 1 hidden layer, 4 neurons, this is going to increase the complexity that the function is able to model. And so maybe it's able to model better the data. And so both the training loss and the validation loss goes down, and also goes down faster than in the previous model. Then you keep increasing the neurons, you go to 32. Again, the functions, the data gets modeled better. And if you add even more, the validation loss will keep going down. But at some point, you also see some diminishing returns. So in the end, by increasing the number of neurons, you increase the complexity, you increase maybe the training time and so on. But maybe the validation loss didn't change much. And so one would think you should try always to use the biggest neural network ever. But this is often not what you're supposed to do for things that we already mentioned in the past, which is for generalizability. In the sense that, as I said, if your model is too big, it's going to just memorize the training set. And then when you give new samples based on the validation set, has not generalized well enough because it's just memorizing by looking at the previous data. And so this causes the problem called overfitting, which is a concept not only related to the neural network, but to statistics and machine learning in general. And so what would you see in case of overfitting? That the model is basically memorizing the data set with time because there are more parameters than actual samples. In the 2 learning curves, in the curve of the training loss and the curve of the validation loss, in case of overfitting, by time, through the steps, what would you see? Overfitting means that the model is basically at some point memorizing the data. And so it's just trying to memorize the data in the training samples, but this information that is learning is not generalizing on the validation set. What would you see in terms of the training and validation loss curves? basically you will see that since the model is big, the training loss will keep decreasing. In the sense that the model is learning well to predict the labels for the training dataset because it's essentially memorizing it because the model is big. Basically, as if every parameter encodes for a single sample, a single cell in your dataset. So the training loss keeps decreasing, but since it's not generalizing, when you give it data that the model has never seen, the validation loss at some point goes up the more the model learns. Because the model learns, if the model is too big, the more it's going to memorize only the training data, not generalizing. So whenever you see this pattern, that the training loss goes down, but the validation loss after some point starts to go up, means that your model is too complex. Again, not only in neural networks, but in general. There are possible solutions. You have some ideas on how to solve this problem? One is to make the model smaller, easy, but there are two possible alternatives. Come on, don't be shy. You can say random ideas, it's not gonna be a problem. Yeah.
Give a number of validation.
Yeah, you can look at the validation loss, and when the validation loss starts increasing, you stop the training. And probably that model would have still generalized enough to be able to work well with unseen data. There's another solution. As I said, there are two.
For the training. Yeah.
Well, you can increase the training data for sure. The more you increase the training data, the more the model can be big. There is another concept that you should know because it's lesson number 2, I guess. Yeah, exactly. You can do regularization. You can penalize the model based on how many parameters it has, and this is gonna maybe leads to a higher loss, meaning that the model is less accurate, but at least it's gonna be able to generalize better. Yeah, and the other approach was early stopping, as you suggested. So to conclude this part, we've seen that neural networks are non-linear models, which are composed of neurons and parameters, which are weights, and they're able to model more complex functions than linear methods. The way they learn is by adjusting the values of these parameters with the objective of minimizing this loss function that one has defined, different between regression and classification, based on the training dataset. And these weights and biases are updated using this concept of the stochastic gradient descent. The hyperparameters are also the ones that minimize the loss on the validation dataset. And then you should, whenever you evaluate multiple models, be it a neural network or whatever other model, you should run the tests for that model only once on the dataset, otherwise you risk of adding biases to your evaluation. This is a nice website to look at the visualization between, let me see, the visualization of how neural networks learn. Right. Yeah. It's a very nice way to visualize how neural networks learn, especially in the context of classification. And you see here the number of features that you have. In this case, for example, are the X and Y coordinates of these points. As you can see here, these points cannot be divided using a line. So again, you need a nonlinear method to be able to discriminate between these two classes of points. You set the number of features which features you want, which is going to be the input layer of the neural network, how many hidden layers you want, how many neurons per hidden layer, and then you see what is the output in terms of classification. So if you see here, you quickly see that these points here get classified as blue and these as orange, and this is basically the boundary of when the neural network is going to predict one class over the other. Here you also see the loss function that went down fairly quickly to do this classification. You have different types of problems of classes here, here, and here. And I mean, you can change the number of neurons, you can change the hidden layers and see what are the differences on how the model learns. For example, this is an example of the XOR problem. This is the one that I was showing here. That you see that these two group of cells, in this case in general of points, have one class and these have another class. And for example, to show what I was mentioning before, if you remove any hidden layer, so again, it's input versus output, and you try to learn the data, the model doesn't learn anything because there is no linearity, no complex function modeling. Then if you add hidden layer, add some neurons, you see that the model starts to predict the labels. Of course, it's not going to be perfect, but the more you add complexity to the neural network, the more it's going to draw complex functions and complex boundaries. If you want to play with it, the link is on the slides.